The following program is brought to you by Caltech.
So I wanted to thank the Keck Institute for making this short course possible for all of us to be here. I think this is really going to be a valuable opportunity for us to get a lot of scientists from different disciplines together. And this is something that doesn't ordinarily happen. This workshop that's following this is organized by myself and John Eiler and John Dankinich. And I think that this is going to be a great standalone series for those of you who aren't part of the workshop. This short course here is called Primitive Bodies, Unlocking the Secrets of Solar System Dynamics, Solar System Origins, sorry. And when you think about that, it's a pretty tall order, but what we're doing is we're getting a group of talks together, leading people in their fields, and these are very diverse fields. And this is in the hope of just giving us some insight into this very difficult problem, so hopefully you can understand it a little bit better. And it'll lead very nicely into our workshop, which is called Primitive Bodies, Science and Instrumentation. So with that, I think I'll welcome our first distinguished speaker, who's standing right next to me, Hal Levison.
Probably a little too close for comfort, eh?
Hal's an institute scientist at the Southwest Research Institute in Boulder, Colorado, and he's also our KISS Distinguished Visiting Scholar in association with our workshop. His principal research is in the area of dynamics of astronomical objects, and his work includes studies of the long-term dynamical behavior of comets, the dynamics of objects in the Kuiper Belt, the origin and stability of Trojan asteroids, and the formation of planets. In 1997, he, with Martin Duncan, predicted the existence of the scattered comet disk. And he's perhaps best known, however, for his work on the early dynamical evolution of the outer solar system, and is an author of the NEAS model, the most comprehensive model to date. So thank you, and let's welcome Hal.
Thank you.
Oh, I'm supposed to put this on you, too. All right. There you go.
Well, I want to thank everybody for inviting me. I think I'm going to learn a lot this week because I know almost nothing about what we're going to be talking about, which I guess makes me an expert. So I'm going to talk about some preliminary results of some work we've been doing trying to incorporate, how should I say this, a heretofore underappreciated dynamical process in the planet formation. This turns out to be right. It's really going to revolutionize, I think, our understanding of when and how the planets formed. So since this is a sort of a general audience, let me start off with a brief review. I don't have a lot of time to do this, of what I call the 6.5 steps of standard planet formation. Of course, when the sun forms, it forms out of a collapsing molecular cloud. In order to conserve angular momentum and get rid of the spin in the cloud, it has to form into a disk. The disk is made of gas and dust. I'm sure you've all heard this before, and the dust starts settling down to the midplane. And that's when planet formation starts. The first step in that is the formation of the first macroscopic objects, planetesimals. When I first gave a talk in this room, I don't know, it was in the late 90s, I had this step up there and I said, and then a miracle occurs. Because at that time, we actually had no idea how you build the first macroscopic objects in the solar system. There's been a lot of really excellent work by many people that has occurred in the last decade or so, and I think the best model going now is one where there's turbulence in the disk, and the turbulence concentrates these small particles in the high density regions that become gravitationally unstable and collapse to form the first macroscopic objects. If this idea is right, the first objects in the solar system are actually relatively big, tens to 100 kilometers in size. After that, then the standard ideas apply that these things grow into the planets that we see by two-body accretion. These things hit each other. This is typically divided into 3 stages: runaway growth, oligarchic growth, and the late stages. And I'll get into that in a little bit more in future slides. That last stage ends up with the solid bodies that we see, the terrestrial planets, Uranus and Neptune. And if these things grow big enough, let's say 10 Earth masses or so before the gas disk goes away, you can get you can get gas accretion directly onto the planets, making Jupiter and Saturn. Finally, there's a new step that's been added, I think, in the last decade. You know, if you think about the processes I've been talking about so far, there's nothing in that process that would lead you to a planetary system that knows it's stable for long periods of time. So these things are probably built, but they're built unstable, and they gravitationally go unstable, scattering these planets around. This probably leads to some of the high eccentricity, large mass planets that we see in extrasolar planetary systems. And in our own solar system, some people now think, I don't think calling it the most comprehensive model to date, the NICE model, is appropriate. There are a lot of people that still don't like it. Makes me actually nervous that it's gotten so popular. But anyway, the NICE model is an example of that happening in our own solar system. So I'm going to concentrate, actually, let me go back, on these steps in this talk and talk about some problems that we have understanding the final growth of the planets. So let's start off with the late stage. In order to understand the late stage, we have to go a little bit back in time and talk about what we call oligarchic growth. As the planets form, they tend to get into a situation where they have a bimodal size distribution. You have a population of growing planets, the embryos or oligarchs, that are fairly tightly packed against one another, embedded in the sea of planetesimals. These guys are jostling one another and want to start competing in order to grow. But there are enough planetesimals in that population to keep everything settled and well behaved. Right? The dynamical interaction between the embryos and the planetesimals act as a sort of drag, and so the embryos are sort of sitting there waiting for the planetesimals to go away. Okay, and they know their time is coming because they're growing by eating the planetesimals. So slowly over time, the planetesimal population decreases. These things are getting bigger. Occasionally they eat one another, but they're fairly tightly packed. And eventually get to the point where there are just not enough planetesimals in the population to keep the embryos well behaved, and then all hell breaks loose. Okay, let me show you an animation by Dave O'Brien that we did a couple of years ago. This is eccentricity, semi-major axis. There are a bunch of objects here. The radius is actually proportional to the physical radius, so he's got a population of embryos, which are big, a population of small guys to represent the planetesimals. I color-coded these around 2 AU in order so you can see how much mixing is done when the instability occurs. And these lines represent the mean motion resonances with Jupiter, assuming Jupiter's on the current orbit that we see it today. Watch, the thing just goes kaplooey. Things start scattering all over the place. You can see there's blue objects here, there are red objects here, so there's a lot of mixing. This is where most people think that Earth got its water, right? That it was from asteroids in the outer part of the solar system. And at the end, you see something that looks remarkably like what we see, right? There are 3, in this case, very relatively large planets. They have a veneer of stuff from the outside. Beyond 2 AU, it's empty, making the asteroid belt. So, I mean, this kind of result we've known for about 15 years, right? That if you just do this, you get basically what we see. There's a couple problems, and the foremost you can see right here. This planet, which is supposed to represent Mars, is the same size as everybody else, right? You do these calculations, and I can show you some results from Sean Raymond back in 2009, where he did a whole bunch of calculations like this and put them all the same plot showing the mass of the planet as a function of semi-major axis. The squares represent the true solar system, and as you can see, I should point out these error bars just measure the eccentricity of the planet, okay? So the gray dots are what you want to look at, and you can see outside of 2 AU, you essentially have an asteroid belt, but in the region between, let's say, 1.2 and 2 AU, all the planets are Earth masses, not Mars. So the fundamental problem that a lot of us have been worried about in the last decade or so is why Mars is so small. Right? I was surprised to see that Mars is actually interesting. So, sorry, where's Jim? I'm sorry. But there's a huge problem with the calculations that I just showed you, and it has to do with the dynamic range of the problem, right? If all the objects in the solar system started off something like 10 to 100 kilometers in size, there are roughly 10 to the 14th objects in the original solar system that we have to deal with. Now, I've been in this game for a long time, and our n-body calculations have gotten better in the 10 or 20 years or more that I've been doing this, right? But I don't think anytime soon we're going to be able to do a calculation that actually can follow 10 to the 14th objects. That's impossible. So, and indeed, there's no single published code that I can think of that can actually go from these original planetesimals to Earths. So traditionally, what's been done in the field is to do the problems in pieces. You would come up with a statistical code that would look at the accretion of small bodies, planetesimals, up to the point where you were oligarchic growth. Then you would put it in another kind of code to do the oligarchic growth. And then you would take the output of that and put it into an n-body calculation to do the late stages, for example, okay? So the calculation that I showed you before started off with initial conditions that look like this, right? This is the output of an oligarchic growth calculation where you have a bunch of embryos, like I said before, embedded in a sea of planetesimals. Although these are pretty damn big planetesimals, they're the size of the moon. It's another problem, okay? But that's the system that they start with. And of course, the problem is that the accretion time is very different in different parts of the protoplanetary nebula. Close to the sun, the densities are much higher, the time scales because of the orbital periods are much shorter. So you would expect growth to occur from the inside out. You wouldn't expect every stage to end at the same place in the nebula. And indeed, here's a calculation from a code that we have that can follow the early stages, showing what you would expect to happen through the region of the terrestrial planets. And you can see that you get growth all the way up to Mars-sized things, or I guess that's lunar-sized things, in very short order at 0.7 AU before anything really happens at 1.5 AU. And I think that this problem, and you can't blame these guys, right? They were doing the best that they could do because of the technical limitations we're faced with, of starting off with a uniform distribution like that is simply wrong, and I think it has led us down the wrong path when it comes to understanding how these objects form. The other step that I want to talk about is gas accretion. If these things can get, if an object can get to something like 10 Earth masses before the gas disk goes away, and that time scale is really very short, right? It's only about 2 to 3 million years, maybe 5. Then you can get direct accretion of gas onto the planets, leading to essentially the formation of Jupiter and Saturn. But there's a problem with this as well. First of all, there's the timescale issue, right? You have to build the cores of Jupiter and Saturn very quickly. But also, there's the issue of what happens when these planets, as they're growing, dynamically gravitationally interacts with the growing planets. This has been known for a long time, that if you have a gas disk and you put a planet in the gas disk, the planet generates essentially waves. These are density enhancements, and they can feel the gravitational effect of these density enhancements and get accelerated by that. And as a result, the planets move around. There are two types. If the planet is small, it doesn't really affect the surface density of the disk. But if the planet is big, you can actually open up a gap around the planet. Okay, and the planet becomes locked to the gas disk and then evolves as the gas disk evolves in the solar system, called type 1 and type 2. This kind of interaction probably is very important in extrasolar planetary systems. It probably caused the plethora of, for example, hot Jupiters that we see in many of these systems. Okay, but I don't think it happened here, and for two reasons. First of all, we don't see a hot Jupiter close to the sun. I think, I'm a theorist, right? So I tend not to trust observations very well, but I think it's pretty sure that we do not have a hot Jupiter, so we can throw that idea away. Although I think it's actually a weak constraint. If you look at the Kepler systems that have been found, right, they see a lot of planetary systems that have big planets very close to the parent star. And I think one thing we as planet formation people have to start thinking about in our own solar system is why that didn't happen here. Why is the innermost planet in our solar system, Mercury, so far from the central star? And I have no good answer for that. But one explanation might be, and again, I haven't worked on this, but it might be that at one time we did have a hot Jupiter that ended up, through tidal interactions, hitting the central star, leaving a gap. Maybe, I don't know. So I put a question mark there. More importantly, I think, what we can say is that I don't think type 1 migration was important here. Right, in the standard model of planet formation, like I said, the cores of the giant planets, which are out beyond 5 AU, started growing first. If type 1 migration were important, when these things got to about the mass of Mars or the mass of Earth, you would expect them to start spiraling towards the sun. If that's true, when the Earth got formed, right, they would accrete a couple of these things, and the Earth would have a 1,000-kilometer ocean, and it doesn't. So the fact that the Earth is so dry, I think, is an important constraint that tells you that type 1 migration probably wasn't important in our own solar system. Now, there's been a lot of work on how do you get rid of type 1 migration, dating back for at least a decade. Okay? We've been working on an idea based on planetesimal-driven migration, sort of counteracting type 1 migration. It's been known since, I guess, I think it was 83, but it might have been 86, that if you take our solar system, as we see today, Jupiter, Saturn, Uranus, and Neptune, but Uranus and Neptune much closer to the sun, and put it in a disk of planetesimals, as the planets gravitationally scatter the planetesimals, the planets move, right? So you end up with something that looks like this. No one really, I should point out, when this was first pointed out by Fernandez Nip, everybody looked at it and went, nah, we don't have to worry about that, right? But it wasn't until the discovery of the Kuiper belt, which has these weird resonance structures, that people started appreciating something like that probably happened in our own system. And I think either it's in these models, something violent, or this smooth migration, it is now widely accepted that the planets moved around a lot in our own solar system due to this process. But people have been ignoring this process when it comes to planet formation. And after all, they say, wow, the gas disk is 100 times more massive than a planetesimal disk, right? It simply should win. And it turns out, though, if you look at this in detail, that may actually not be true, right? And we should have known that. If you go back to sort of the classic works on this and ask what they say the time scale for migration should be, for type 1 migration, right, if you take a 1 Earth mass thing and a minimum mass solar nebula at 5 AU, it takes roughly 1 million years for that to migrate into the sun. But if you look at the classic works on planetesimal-driven migration, put it in the same form, this would predict that planetesimal-driven migration to drive this thing into the sun in only 10 to the 5th years, almost an order of magnitude faster, all right? And this scales as the mass of the planet. So it's even worse for something like Mars, almost 2 orders of magnitude faster due to type planetesimal-driven migration than type 1 migration. And indeed, when we put both of these in to n-body simulations, planetesimal migration usually wins. Here's a quarter of an Earth mass object embedded in a 5-time minimum mass solar nebula at 5 AU. We have a torque on this thing that's trying to pull it in due to type 1 migration and the planetesimals, and you can see the planet actually moves out, okay? So planetesimal-driven migration usually wins in these calculations. Now I have to give you a caveat. Okay, all we did in this calculation is we took an n-body code and we put a torque on the planet that mimics type 1 migration. No one has yet done a calculation with both hydrodynamic gas, right, and planetesimals to see if this is actually right. And Morbidelli, Nesvorny, and I are currently starting to do this, but we have no results yet, okay? So it could be there's some nonlinear effect. For example, that as the planet starts to move, it has to drag the gas along with it, increasing its inertial mass, which could affect these results. So you have to take all this with a grain of salt. But if you believe it, I can do some really amazing things. So let's talk about Mars. As I said before, one of the biggest problems with the current models is that the object that we build at 1.5 AU is too big. And also, as I said before, but all these calculations assume that everything formed at the same time, and as a result, there can be no migration by definition. Fortunately, we still don't have a code that can do this problem right. So we decided to attack it in pieces. The first thing we did is developed a new Monte Carlo code where we can handle growth correctly, and I'll show you some results of that in a couple of minutes. But we can't handle dynamics correctly, right? So we don't get migration. But we can check to see if the conditions are right for migration to happen. Then if we take these candidates where migration, we think migration can happen, and put it in an n-body code and then watch what happens. That's essentially what we're doing. In order to check whether migration can happen, we have to come up with some criteria. We did this by a bunch of n-body simulations, and we came up to 4 criteria that must be met in order for migration to happen. I'm not going to go through these. I really don't have the time, except to point out that one of these criteria has to do with the eccentricity of the disk that you're embedded in. If the disk is dynamically excited, you can't migrate. Okay, and that's going to become important in a couple minutes. So we sit down, we take our n-body code, our Monte Carlo code. In this case, we actually start off with real planetesimals. The calculation I'm about to show you has 55 million planetesimals that have something like a radius of 50 kilometers to start with. That's roughly 2.5 times the minimum mass solar nebula. And we sit down and we just actually, based on the local conditions, we actually merge them together, right, to build bigger objects. So we're actually getting the statistical variation, which is what's important here, in the growth of objects as a function of time. The velocity evolution is handled entirely analytically here. So we're not doing any real dynamical calculations, and so we get no migration. But what I can show you is the results of this calculation. Here's the mass as a function of semi-major axis. Most of the particles are below this curve. Like I said, there are 55 million of them, but I'm just showing you the upper branch of that. And as these things grow, I'm going to flag them and turn them red when they satisfy our 4 criteria for migration. Okay? So as you can see, you're getting essentially a growth front moving out through the inner part of the solar system, and every once in a while, one of these guys can migrate. Okay? And notice that they can't migrate in because they run into another guy. What they do is they'll migrate out. Typically, as I said, we find roughly a few candidates per run. Their mass is roughly the mass of the moon, and they tend to grow between 0.8 and 1.2 AU. And watch what happens when we put that in an n-body calculation. Here is, again, eccentricity versus semi-major axis. And the radius of these things are going to be proportional to their true radius, and their color is going to be proportional to their mass. So they all start off around the mass of the moon. And as you'll see, in very short order, the outer guy takes off, migrates through the disk, and grows very quickly to the mass of the Mars when it hits 1.5 AU. Now, remember I said that these, well, let me take a step back. So this growth rate is actually incredibly fast. It's much faster than you would get if you just put this object in a disk and let it accrete. And the reason is that the accretion rate is a strong function, again, of the dynamical state of the disk. If the dynamical state is cold, meaning low eccentricities and inclinations, you can grow like mad. And if it's hot, growth is essentially frustrated. In this case, what's happening is the migration rate is so fast that it can migrate faster than the planet can stir its suit, can stir the planetesimals. So as it's going through this disk, it's always running into virgin cold disk, and therefore the growth rates can be enormous. Okay? It's sort of like a shock front going through. It hits the fresh material before the fresh material even knows it's there. The other interesting thing about this result is, like I said, we got a Mars mass object at the end. You may be thinking, yeah, but that probably depends on things like the surface density of the disk and how much material there is and things like that. Turns out that's not true. The migration rate and the growth rate both scales the same factor of the surface density of the disk. So if you up the surface density of the disk, everything happens faster, but you always end up with roughly the same mass. So not only do we get a small mass from Mars, but to 0th order we reproduce Mars's mass and can predict what it is. So now let's take a look at the system. The next issue is, what do we do with this stuff? Because there's a hell of a lot of mass there. And it turns out that this is so dynamically excited that when they hit, it grinds down rather than accretes. So if we just take, let's say, this outer part of this and put it into an accretion code, we find that the planetesimals actually grind down before they can accrete each other or before this outer embryo, this Mars, can concrete the material, and it essentially grinds to dust. So you end up with this isolated Mars out here, a large gap. There may be another planet in here or not. Dave Minton wants to think that this is the thing that actually ended up making the moon and the moon forming impact. I don't think that's a little extreme, but you end up with these isolated guys. And in here, you still end up with a dense population of embryos, which will later merge to form Earth and Venus in the standard violent way. So we can explain Mars's mass. Most of this material Mars is made out of is accreted from out here. So if there are any chemical differences between the Earth and Mars, we can get that. And this happens very fast, so we can explain its old age, which Mars is fairly old. So it's pretty successful. Okay. Yes?
Is stirring from gas turbulence included?
Yes, this is all turbulence? No, we haven't. We assume quiescent. Aerodynamic drag are in these calculations, but we don't have any turbulence.
Hal,
Yes?
why doesn't Mars continue to grow as it moves through the planetesimal disk? Why does it stop at 1.5?
You're way ahead of me, eh? You usually are. In that particular case, I was actually just going to ask that question. In that particular case, Mars stopped migrating because it hit the edge of the disk. Okay? So well, we wanted to know what Mars would look like, right? So the question is, what happens if we don't do that? Now, I must admit, I'm a little intimidated by this. This is a pretty radical idea, and I'm worried about your response. So if you give me a second, I'm going to prepare myself for your reaction. Okay, I'm ready. No, you guys can't hear me, can you? So I'll take it off. So the question is, what happens if we don't put that disk edge in? So let me show you the same calculation. Okay, we're starting off with a lunar-sized thing and 1 AU. Putting it in, this is pure n-body calculation, an extended disk going all the way out to 20 AU, and I'll just let this speak for itself. Okay, it started off slow, right, and then it hit the snow line, and that's why it accelerated, right? So we end up with a 17 Earth mass object. Does that sound familiar to anybody? By the way, we didn't fine-tune the initial conditions to get this. Okay, that's the mass of Neptune at 20 AU from this simple calculation, right? And again, it grows like mad because of this idea that it's migrating through a cold disk. It's almost like a shock. And if you vary the initial conditions, what you see here are various plots showing semi-major axis as a function of time, mass as a function of time for a 2 times minimum mass solar nebula, and a 2 and 4 times snow line, density enhancement at the snow line. And as you can see, in almost all cases, we build essentially things comparable to the mass of the giant planet cores, right, in very short periods of time, less than 1 million years. So this solves, this is right? This solves the long-standing problem with how you build the giant planet cores fast enough. So you can see why I need my helmet, right? So we can come up with a fairy tale. And I have to tell you, we haven't gotten very far with this, okay? And right now we've only done migration of a single planet through a disk, okay? That code that I showed you actually is very complicated because it requires a lot of particles in the disk, and we have yet to extend it to a multi-planet situation. But you could come up with a story, right? And the story is planets start to grow. They start growing from the inside out. A guy somewhere near 1 IU gets to the point where it can migrate. Goes ping out through the disk, right? Going all the way out, it becomes Neptune, right? But it dynamically excites the disk, so the next guy can't migrate yet. If gas is still around, the aerodynamic drag between the disk particles and the gas will cool off dynamically cool off the disk. That'll allow migration to happen again, and ping, through the disk. Here comes Uranus, right? This happens again, Saturn. And the fourth time is when the gas disks start going away, so Jupiter can migrate, right? But it leaves a hot disk behind. And that hot disk, Mars starts to try to migrate and is frustrated by the fact that it hits a dynamically excited part of the disk and it stops to become Mars. That's the basic story. I have to tell you, we haven't done most of this yet, right? And I'm actually talking about it because I think it's such a cool idea that I want everybody to know about it, even if it turns out to be wrong, right? But there you go. So there's some implications of this that are quite stunning, right? First of all, if this is right, Neptune is the oldest planet in the solar system, right? When you say, well, wait a second, if Neptune's the oldest planet in the solar system, why didn't it get a gaseous envelope like Jupiter and Saturn? And we think we have an idea for that. If the sun were part of a large star cluster, which we think it was due to the aluminum-26 and other characteristics. We just had a paper arguing that the gas disk must have been truncated inside of 60 AU based on the dynamics of the Kuiper belt, for example. Then UV radiation from the massive stars will photoevaporate the outer parts of the disk. This has been well known. My postdoc, Catherine Kretke, has been building models of this. And essentially, what she finds is something that looks like this. Surface density is a function of time. This is a 2.5 minimum mass solar nebula with an alpha of 10 to the minus 4, a half a parsec from an O star. And I'm going to show you her model, which models the change in the surface density of the gas disk coupled with the migration simulation that I just showed you, okay? So we turn on the star, put the planetesimals down, turn on the star. Here's my Neptune coming out, and the disk is photoevaporating away. And Neptune moves off the outer edge of the disk. So that's essentially our idea, that Uranus and Neptune migrated off the outer edge of the gas disk and therefore did not accrete massive gaseous envelopes, while Jupiter and Saturn stayed in the disk at the end of their migration and therefore did. Again, we have a lot of work to do on this model before we know whether this works. I should point out, though, she looked at the accretion of gas in this simple model that she wrote onto this planet. Let me show you the results of that. Here's essentially my solid accretion model as a function of time that I've been showing you for this is the third time. Its mass is a function of semi-major axis. And this is what she finds for the gas accretion. And again, we get something like a 15 Earth mass object off the edge of the disk that's accreted around an Earth mass of gas, which sounds pretty much like Neptune to me. Okay, the other thing is that Jupiter forms just as the gas disk is going away, which is why Mars can't become a gas giant. This might explain why it is so metal rich. And we also predict, and I put a question mark here because, again, we haven't done multi-planet case yet, that the core mass of planets should increase with heliocentric distance, and the zeroth order, that's what we observe. So I think I'm done. This is a PDF file. You can download it from here if you want to look at it some more. I'm a soft money, so I have to thank my funding agencies, NASA and the NSF, for this. This just says what I already said. So thank you.